So in this video, we're going to find a formula for the area of a triangle. And you might already know it, but I'm going to show you how we can find it. And the first thing to start off with is when we say triangle, I pretty much mean any triangle. It could be a right triangle, an isosceles triangle, a scaling triangle, any triangle. And so we're going to find the formula for the area of any triangle. And what you're going to start to realize is if you're trying to find it, it's probably pretty useful to find the formula for the area of a right triangle first. So let's start with a right triangle and see if that will help us. Now, a right triangle, let's just say we have a right triangle that looks like this. A right triangle that looks like this. And I'm going to call this right triangle ABC. So this is triangle ABC. Okay, so we have right triangle ABC. And I'm going to call this length B and call this length H. So then what is the formula for the area of this right triangle? So what's the area of this right triangle in terms of B and H? And we know this is the base of the triangle and this is the height of the triangle, right? Now, some people, and this is probably the way I would do it, is they'd be like, well, what if I form a rectangle? If I were to extend a line this way and a line this way so that I make a rectangle at point D right here. And if I'm making a rectangle, how do I exactly know if I'm making a rectangle or not, right? I can't just say, oh, I made a rectangle, right? There's no way to say that you made a rectangle. But here's the thing you do know. You know that you're constructing segment CD in such a way that it's parallel to AB. So AB, let's just do this, AB is parallel to CD. So that's how you're constructing that line. Another thing, I'm constructing AD in such a way that it's parallel to BC. So these two lines are parallel to each other. Okay, so that's how we're constructing them. Now, you can see that quadrilateral ABCD is a parallelogram because the opposite sides are parallel to each other. The opposite sides are parallel to each other. And so that makes this quadrilateral right here a parallelogram. A parallelogram that contains a right angle is a rectangle. So that means all of these corners have to be rectangles. And so you know that you made a rectangle. And so why is it so useful that we make a rectangle to find the area of ABC? Well, the reason why is because if I have a diagonal here, right? Diagonals connect the opposite corners of a rectangle, right? We know that we could prove that triangle ABC is congruent to triangle CDA, right? We could do that. We know that these two lines are parallel. So we know that we could say that these angles are congruent. So this angle is congruent to this angle. And we could also say that this angle is congruent to this angle. So we know all these angles are congruent, but that doesn't prove that the triangles are congruent. But we know we have the reflexive property. And so you can say, oh, we have angle side angle congruence, so ASA. As you can see, this, right? So let's just first make that statement. I know that I'm not doing a formal, full-on proof. That would be a waste of my time. But you can really see how this is really happening. So ABC, triangle ABC, you can just pretty much figure this out. Triangle ABC is congruent to triangle CDA. And it's by ASA congruence. So angle side angle congruence. Okay, yeah. Now that we know they're congruent, if these triangles are congruent, doesn't that mean the area of these triangles are the same? So the area of triangle ABC is equal to the area of triangle CDA. Their areas have to be equal if they're congruent. I mean, that just kind of makes sense, right? So we can just kind of use that. I don't know the theorem that says that, but it just makes sense, right? Now another thing is that if you add these areas together, if you were to add these areas together, so I'm just going to add them together now, I'm going to get the area of the rectangle. And isn't the area of the rectangle just base times height, right? So I'm going to say this is equal to base times height. Another thing, these areas are the same exact value. So that means the area of triangle ABC is equal to the area of triangle CDA. So I can replace the area of triangle CDA with the area of triangle ABC because they're the same thing. They have the same area. And I know that if I were to add these two things together, it's really just combine like terms. And you get 2 times the area of triangle ABC. And we just divide 2 on both sides, and you get 1/2 BH. So this is the area of a right triangle. So this works for any right triangle. 1/2 times whatever the base is times whatever the height is. So we found that the formula for the area of a right triangle is 1/2 base times height. Okay, or in other words, let me just draw a quick example. If we have a right triangle, it's 1/2 times the base times the height. So the length of one of the legs times the length of the other leg, 1/2 of that, right? Or pretty much like half the area of a rectangle form of it. And we saw that. Now we can use this idea to find the formula for the area of any triangle. So let's just say we had a triangle that looked like this. And it's not going to be a right triangle. So it's going to be any plain old triangle. And so it looks something like this. And I want to know the formula for the area of this triangle. So I want to find what the area of this triangle is. Now let's just say we draw an altitude. And I'll call this the height of the triangle, right? Assuming that this is the base of the triangle. Now what I'm going to do is I'm going to use side lengths in order to do this. I'm going to use points in order to represent my line segments. So, yeah. What can I do in order to find this? Well, to find the area of this entire triangle, I see that when I made the height, I pretty much made 2 right triangles, didn't I? So I could add the area of this triangle plus the area of this triangle. So the area of triangle ABC, so the total area of my triangle, my total area of my triangle is equal to the area of that right triangle plus the area of this right triangle. So I'm adding these 2 regions up to get the area of my triangle, right? And since we know the area of a right triangle, we can use that to find the area of any triangle, right? And so you can try that. So how would we find the area of 1? Well, remember, it's just going to be 1/2 base times height, right? So it's going to be AD, 1/2 AD times DC. So it's 1/2 AD, I'm going to do this, 1/2 AD times DC. And then I'm going to add that to the area of the second one, which is still, again, it's a right triangle, so it's just going to be 1/2 base times height. So 1/2 BD times DC. So 1/2 BD times DC. What do you notice? What can we do with this? Is this our final answer, or is there something we can do with this? Notice how we can factor out 1/2, and we can also factor out DC. And that's a very cool, really important thing to realize. So we're going to factor out 1/2 and DC, right? Because it occurs in both of these terms. So 1/2 times DC, oh, that's not it. 1/2 times DC. Remember, if I'm pulling out a 1/2 DC, I'm left with AD right there. So I'm going to have an AD plus BD, right? Now, what's AD plus BD? That's the base of my original triangle, right? That's the base of this my entire original triangle. So really, the area is just 1/2 DC times AB. Now notice how I get 1/2 AB times DC, and normally we call this the base of our triangle, right? The base of our triangle would be AB, and the height of our triangle would be DC. So base times height, right? So the area for any triangle that looks like this is just 1/2 base times height. It works for any triangle. right triangle, and any triangle besides a right triangle.